Good afternoon, everyone. We'll get started. Welcome to today's i4Energy seminar. My name is Gaiman Yi. I'm with the i4Energy Center. And today's speaker is Lindsay Miller. She is a postdoc here at Berkeley, where she recently completed her PhD in mechanical engineering. Prior to Berkeley, Lindsay earned her BS degree in mechanical engineering from Case Western Reserve University. Here, her current research is in piezoelectric vibration energy harvesting for wireless sensor networks, and in particular, she's focused on methods to passively self-tune the harvesters to the vibrational frequency. So let's welcome Lindsay and her talk today. Thank you.
Thanks, Gaiman. Let's see. Okay, so today I want you guys to ask questions anytime that you have something that you don't understand. I think it's a lot more interesting to follow a talk if you understand what's going on along the way. So, and I'll repeat your question so that Gaiman doesn't have to run the microphone around if you have a quick one during the talk. So as Gaiman mentioned, today I'm going to talk about the research that I've done in energy harvesting. But I'm also going to talk about, just really briefly, the work that goes on in our whole lab with energy harvesting, because my work is only a piece of the type of energy harvesting work that we do. So I didn't list everyone up here on the slide, because almost everyone in our lab's work is shown really briefly here. But just know that it's a big collective effort. And I'll point out when I switch to my specific research. So just real quick for motivation for energy harvesting, there's a huge potential for using wireless sensor networks for improving the efficiency and quality of manufacturing operations and enabling energy efficiency and demand response in buildings, and implementing smart grid and other kinds of sort of futuristic and next level energy systems and infrastructure systems. But for these things to be successful, these wireless sensor networks, they need to be essentially maintenance-free. They need to be low cost and have a long lifetime. And right now, wireless sensor networks are powered by batteries, and these have not proven to be sufficient for meeting the needs for applications of energy harvesting. So, or for wireless sensor networks. So energy harvesting has a potential to fill in some of the weak points where batteries alone have not managed to make wireless sensor networks easily deployable. So when I talk about wireless sensor networks, this is what I mean. It's a node that has some sort of power supply, which for us, I'll be talking about energy harvesting, power conditioning, and energy storage. But this could also be just a depletable battery, and then a sensor and a radio. Those are the general components of a sensor node. And some examples from commercial nodes are dust networks, which many of you know of. Professor Chris Piester from the EECS department here started this. And dust networks' big thing is that they make the configuration of the wireless sensor network almost essentially automatic, so you don't have to do a lot of, there's not a lot of headache with installing the actual wireless sensor network. And those are typically powered by coin cell batteries or solar cells, depending on the application. And then these crossbow motes give you some other idea. These are coin cell and AA battery powered. And you can see that especially in these, the power supply is more than half of the volume of the device. And then here's another example of a more recent energy harvester powered node. This is a National Instruments sensor node connected to a Perpetuum energy harvester. And this is an electromagnetic energy harvester that weighs about 1 kilogram. It's about the size of a soup can. And you have to have a pretty involved bolting onto a motor. The installation of this is pretty involved. It's not really what is ideal for energy harvesting and sensor nodes, where you'd really like to be able to just Velcro, stick something on where you want it, and then leave it and forget it. And but this is one of the first examples in the commercial market of an energy harvester that's actually being used. So the other thing I want to point out before I get into all the details is that there are lots of different ways to harvest energy, and I'm not going to say that the way it's hard to say that any one way is better than other ways. It just depends on the application. So keep that in mind when we're looking at all these things. It's possible that you can use multiple types of energy harvesting in one sensor node even. So you want to be open-minded about the types of energy we're going to harvest. So the structure of my talk today, first I'm going to talk about what research is going on in our lab group in these 3 areas of energy harvesting. And that'll be sort of general stuff. And then I'm going to focus in on vibration harvesting, since that's what my research has been on. And I'll get into more of the details there. So to start with, a group in our lab works on thermoelectric energy harvesting. And again, stop me if you have any questions while I'm going through this stuff. I'm just going to briefly describe how the energy harvesting works and what's the sort of novel thing that our lab group is working on for each of these technologies. So for thermoelectric harvesting, it works using the Seebeck effect, which is when you put 2 dissimilar materials that are thermally in parallel but electrically in series and apply a temperature difference over these materials, then you produce a current. And when you put a resistive load in that current path, you can get power out. So in our lab group, the novel thing that's being done is printing these thermoelectric materials through a dispenser printer, and I'll talk more about that later. But what this allows you to do is really optimize the length of these couples in the thermoelectric device, and that is very important because MEMS thermoelectric harvesters are so thin that you don't get a lot of delta T over the couple, and macro scale couples are so thick that you end up losing a lot of heat to the environment. So the printer system allows you to have very customized, optimized, ideal thickness films. It also allows you to print on almost any substrate, including flexible substrates, and it allows you to print in any kind of customized pattern very easily. So a lot of the research is around the printing methods in sort of a manufacturing sense, as well as the material science of developing these thermoelectric materials. And then electromagnetic energy harvesting is a type of vibration harvesting, and it works by basically having a magnet that moves with respect to a coil. So in this case, instead of having a temperature as a thermal source as your energy source, you have vibration of some kind. And you can either have the vibration move the magnet, which is on a spring, or you can have it move the coil. But as long as they're moving with respect to each other, typically they use the magnet as a mass so that you attach that to a spring, and this oscillates. And then that generates a current. And so Andrew Waterbury has been working on this really cool 1-inch cube device. And he's done a lot of optimization. And this is a very neat design. He's been able to harvest more than 1 milliwatt from ambient vibration sources. So he actually put this on a motor and was able to harvest that much power. And this is the work that I do, and I'll get into more detail about it later. But in general, piezoelectric energy harvesting works by using a piezoelectric material in a spring structure so that you have vibrations excite the material, and when the material is deflected, it produces a voltage. When it's deformed, it produces a voltage. And so then if you make a structure like this, which is picture a little diving board where this square is like a mass, it's like a person jumping on the end of a diving board, and when this is mounted on a vibrating source, the beam fluctuates up and down, and that strains the piezoelectric material, thereby producing a voltage. And then along the lines of piezoelectric devices, but using airflow instead of vibrations as the source, a couple of students in our lab have designed this very cool flow harvester that you can put in an air duct. And so the way this works is this is a blunt obstacle. So this is a cylinder in this case, and the little piezoelectric beam, and then a big balsa wood fin at the end of it. So in this case, instead of having a mass at the end of the beam, you have this fin. And as air flows through the duct, vortices shed off of the cylinder at regular intervals, and they essentially pluck the end of this beam and allow it to oscillate back and forth. So you can design this so that these fluctuate off at the same resonant frequency as the device. And they were able to generate, again, about 1 milliwatt from 3 meters per second airflow, which is a standard duct airflow. So this was a very cool little proof of concept they did. And then this is another really interesting project that's been going on in our group for a while. This is using a piezoelectric beam similar to what was in the previous 2 slides, but harvesting from the AC current that flows through power lines. And the way this works is using a magnet as the tip mass instead of the fin, or instead of just a heavy object. They use a magnet, and that couples to the AC magnetic current field that's going through the power cord. So here's a prototype that's been built, and here's another a prototype, and they're getting almost a milliwatt out from currents flowing through those power cords. So this is really cool, and there's a lot of interest in the smart grid for using these to sense in electric power infrastructure.
Question.
Yeah.
What kind of current is necessary for the device to be drawing to get a milliwatt out?
That's a great question. I'm not sure, but I know like these kind of zip lines, like what go to a lot of appliances, are sufficient. Igor, do you have any quick answer to that?
So what was the question again?
It was the.
I mean, what kind of current draw, what kind of power draw must the appliance be using to get a milliwatt out?
Milliwatt. So it depends.
Well, this was with 5 amps RMS, and so that's pretty, I guess, pretty high. But the big power lines will obviously have huge current going through them, so that's easy.
You can optimize the device to get 1 milliwatt out of this amount of current. And we've seen, from 10 amps, 1 milliwatt easy, but that's unoptimized. So it's on this order.
They'll practically be on the 10 amps to give you an electric space heater or something.
Right.
So that's a powerful device.
Yeah. Thanks, Igor. Okay, and then so I've been talking about all these different ways of harvesting energy, and I haven't talked yet about how much power is needed by the thing we're trying to harvest for. So before I get into numbers, I wanted to just lay this out. I showed you all these blocks in the previous slide, but I wanted to make sure you understand the direction that energy flows in the sensor node. So first, the harvester generates energy and from whatever the ambient input source is, and then a power conditioning circuit adjusts that energy signal so that the energy storage component can accept it and store up some energy. And then a power management circuit steps that voltage and current signal to whatever the specific sensor and radio need. So when I talk about load, I'm meaning the sensor and the radio. And when I talk about the sort of hybrid power supply, it's these 3 blocks that can essentially, these are what would replace the depletable battery that's used today. So then just to get a sense of what kind of power we need for these sensor nodes, this is a sort of state-of-the-art called PicoCube radio that was developed here at Berkeley at the Berkeley Wireless Research Center. And this node required about 5 milliwatts peak and 5 microwatts on average. And it achieved that. The difference between peak and average is because peak is what's required to send or transmit a signal, and average is what it ends up being if you look at the duty cycle of how often you send a signal. So, so for a lot of the applications, whether or not you can end up generating enough power to power the sensor node is dependent on what duty cycle you need for the application. If you have to send multiple signals every second, that's going to be a harder application than if you can send 1 signal a second or 1 signal every few minutes or something like that. So the minimum that I have here of a microwatt at about ½ a volt is based on the fact that the power conditioning circuit requires basically ½ a volt at about a microwatt in order to actually condition the power and to overcome the threshold voltage of some of those circuit components. So this is the bare minimum you need to do something useful to actually start charging the battery or capacitor, and this is what you actually need to be generating to really power a state-of-the-art low power, ultra low power sensor node. And keep in mind that in a lot of applications you would need to have more than just 1 sensor, or there may be other things you want to add on that might increase this power a little bit. Okay, so now I've talked about the background of this, and I'm going to start talking about ambient vibrations and then the MEMS piezoelectric harvester. Okay, so before designing the MEMS piezoelectric harvester, it's important to understand what actually we're trying to harvest. So I did a survey of a bunch of different vibration sources in Echeverry Hall across the street and surveyed about 20 or 30 different pieces of vibrating equipment in Echeverry Hall. And so this is an oil compressor mounted on a platform. This is a fan belt that drives this duct fan, and then ductwork comes out from it. And then this is a chilled water pump. So basically everything in the machine room vibrates. I hadn't really fully realized how much everything is vibrating in there until I started doing this survey. But it's not just the motor that vibrates. It's everything connected to the motor. It's the floor next to the motor. It's not just that this fan is vibrating as the belt goes around, but all of the ductwork is also vibrating, and the pipes that lead out of here are vibrating. So it's a really rich source for harvesting energy in here and using that to power sensors. So then this shows you how the accelerometer, and then inside this Faraday cage box was my little MEMS harvester right there. This shows you how the setup was configured. And then the main findings from this survey were that the vibrations are low amplitude, typically 0.1 to 0.01 G, low frequency, under 200 hertz, multiple frequency, not just a single sine wave, and also time varying. So those 4 characteristics of ambient vibrations are really important to keep in mind as we start working on the design phase. And this just shows a power spectral density of a couple of the different sources. This is that fan belt cage and the oil compressor. And what I'm trying to show here is that, first of all, above 200 hertz, you have very little, you have pretty much zero energy in the vibrations here. And here you have some, but the dominant is under 200 hertz. So in general, basically all of the vibration sources were similar in the sense that all of them are low frequency dominated. And then also the frequencies that are dominant here, if you zoom in to this low frequency range, are very different. So what this points to is that you can't really have one harvester that's optimized at one frequency and have that work on any machine. And so that's important to keep in mind for later as we'll be working on this. So in designing my first MEMS device then, the goal was really to have a low frequency device. And anyone who's worked with MEMS knows that, or vibrations, as you scale down the mass and the length scales, it gets very hard to have a low frequency device. And so I had not read about something in the literature that had a resonant frequency MEMS device under 200 hertz. So the first goal was to sort of see if this was possible. So real quickly, the MEMS fabrication steps that I used to build the first device. I started with a blank silicon wafer, which is gray, grew a thermal oxide layer, which is the blue color, then sputtered a titanium platinum bottom electrode, which is red, and then sol-gel spin deposited the piezoelectric layer, which was PZT. It's lead zirconate titanate, and that's the orange layer. So then the first masking step was patterning chrome palladium top electrode, which is checkered here, and then etching with HF to reveal the bottom electrode, and then another etch using argon ion milling to reach down to the silicon layer, then backside etching to remove the oxide and silicon, and then this big chunk becomes a mass at the tip of the beam. This becomes the beam. And then final step was to etch away this little connecting silicon layer to leave a freestanding beam. So then this is the beam with piezoelectric material. This is the proof mass at the end. And then here are the electrode contacts. So here's what they look like. This shows how they lay in plane, and they actually hang down a little from the weight of the mass. And the big square, like I mentioned before, is the mass area, and then the trapezoid or rectangular beam is the piezoelectric spring. And this shows the wire bonds to connect it to the substrate, and then here's just a little resistor and test circuit. So these devices did range from 31 to 232 hertz in resonant frequency, depending on the design, and that was the lowest that have been reported for a MEMS energy harvester. Then just to give you a better sense of that, so in this picture you can see the area really easily. And you can see these are 6 millimeters long, which is quite huge for a MEMS device. Like the fact that you can actually see it on the substrate like this is very unusual for a MEMS device. And the reason, like I said, is because the frequency decreases as you increase the length and increase the mass. So also you need to keep the thickness very thin, which is part of why I wanted to use the MEMS processing. So here you can see this is the cross-section of the beam. I basically broke it off at the base. And then this is the mass. So you can see how thick the mass is compared to the beam. And this is the piezoelectric layer with the oxide underneath it. And then here you can actually see the different layers of sol-gel PZT that were spun on. And the way it fractured here, you can actually very clearly see those. And then this is the silicon that has been etched using xenon difluoride. It creates this pocked look. It's kind of cool to look at under the microscope. But yeah, just to give you a sense of what the cross-section looks like.
What about fatigue?
Yeah.
These things are out there for years and years.
Yeah, it's a good question. So I can tell you some of the ones that I made fatigued very easily, and some of them were surprisingly robust. Like I dropped a whole tray of them, and a bunch of them survived. And part of that is based on design. So there's like design flaws or fabrication flaws in some of them, which create stress concentrations and things like that. So another thing is you can do simple things like filleting the corners and things so you don't get stress concentrations there. And then if you package a device so that it has end stops to its deflection, it can be quite robust. Silicon is a really good mechanical material, and so if it's well designed and has these end stops, I think the failure by mechanical fracture, I think, is very manageable, and I'm not concerned about it. I'm a lot more concerned about failure of the PZT material. And that's a much more sort of a whole PhD on its own, so it's not something I focused on. There are people researching it, but what happens is when the PZT cycles over and over and over, it can sometimes lose some of its polarity, is sort of its piezoelectric properties. So there are a lot of people researching that to improve the properties, and there are ways to mitigate that too. But that's, I think, my bigger concern. Oh yeah, and for anyone listening, since I forgot to repeat the question was about fatigue and failure of the device. OK, so then I already showed you the pictures where I had the energy harvester mounted on ambient vibration sources, but this is the data from those experiments. And what this is showing, it looks like a mess. It's a very busy slide, but the point is that this peak is the energy harvester output. So the point is it generated some power, and the other point is that the model matched the experiment pretty well. So this is measured acceleration, and the blue is measured harvester output. Then the red is the predicted harvester output by the model. So when you zoom in, you can see that the model and the harvester were pretty darn good comparison. The reason that they diverge at these low magnitudes is because this is the noise level of the measurement equipment. So you can't detect signals lower than that. And then the other thing I should mention is that this model was unique in that it was able to accept measured ambient vibration input into the model and spit out what the harvester output should be. That was something that hadn't been done in the literature either. So now that gives us the ability to basically perform an optimization using any input acceleration that we want to, even if it's measured from machinery. So the power output from these was in picowatts to nanowatts range when mounted on ambient vibration sources, and that is too small to use for a sensor node, but it was a really exciting proof of concept, actually. I was really thrilled when I got these results, because no one had shown that you could use a MEMS device on ambient vibration sources and actually get power out. It was all kind of hypothetical to use the MEMS device for that at this point. So it was enough of an exciting proof of concept to motivate me to keep working on the next generation and improve the design. And so the next step then, well, first, OK, so I'll talk later about optimization. But first, I want to talk about once you get energy out of the harvester, then as you saw from the diagram of the energy flow through the sensor node, the next step, eventually, it needs to be able to charge up an energy storage device. So some people in our group work on printed batteries and capacitors in addition to printed thermoelectrics. So I partnered with a couple of different students in our lab, including Christine Ho and Alec Chen. And this is the dispenser printer. And the goal was to print the energy storage component onto the substrate that has the energy harvester, which is what you see happening here. So the way the printer works is it's a pneumatic printer, and it can print you basically start with a polymer resin and add ground up active particles that are ball milled to whatever diameter you want, and then mix those together to create an ink. And that ink goes into a dispenser printer tip, and then it's pneumatically dispensed onto a substrate. And what's cool about this is you can use any active particles you want. So it can be, as I have up here, it can be electrochemical materials, thermoelectric materials, magnetic stuff or just heavy materials. You can do any. It's a very, very flexible system. And you can print in different patterns and on any substrate. So it's a very interesting and versatile setup. So this is showing how it works when you print a battery or capacitor. This is the work of Christine Ho and Joe Wang. And it works, you can print layer by layer, just letting the layers dry in between. So like for Christine's multi-layer capacitor here, it was a nickel current collector, a carbon electrode, and then another carbon layer, and a top nickel current collector. So this is the sandwich structure that you see printed on the devices in this slide. So the silver you see is that nickel current collector. And so this is just demonstrating that it's pretty easy to mechanically integrate these two components, the energy harvester and the energy storage component. The thing to note is that since the output from my devices was in such a small range, nanowatts basically, it's not enough power to overcome the power conditioning electronics in order to charge the energy storage component. So these are not electrically connected, but this is a demonstration of how we would do this when we want to integrate these. So the cool thing is you can picture then using this with a chip about maybe the size of the tip of this mass or smaller for the power conditioning electronics. And you'd need some inductors, so that would require a larger volume. But you can see that instead of having 2 AAA batteries, if you could end up using a chip that's 1.3 centimeters square that would be the power supply, and with another small chip for the power conditioning electronics, you can see how that could end up being very attractive to use for wireless sensor nodes. Another cool thing we did, and this was specifically with Alec Chen, is print on the tips of these released cantilevers. So you can see this is before printing a drop and after printing a drop. So as opposed to the previous slide where we were printing in the solid area around the beam, in reality you wouldn't want to use silicon real estate to print like this because silicon is expensive. And you'd rather be able to print on space that you're already using for something. So we were just sort of playing around with printing. These are actually just zinc and epoxy. But what this can do is allow us to further decrease the resonant frequency of the device and customize it if we want to after all the microprocessing is finished. So, and it also, as you increase the mass, the power increases. So this could be a way to basically increase the power and reduce the frequency without having to make a bigger silicon mass. The other thing is you could imagine potentially one day printing electrochemical materials here so that your energy storage component is actually the proof mass of the harvester. OK, so then I mentioned a little bit about why it wasn't possible to electrically connect the harvester with the energy storage component yet. And I wanted to just really emphasize why that was. And so basically, for the power conditioning electronics, for the diodes, well, OK, let me start with these plots, because this will give you a better sense. These plots are showing the output from these different blocks. And so what you see from the harvester is you get an AC output. And it's actually usually a messy AC signal, not a clean one like this. And yet the energy storage component needs a DC voltage of a very specific range. So what we need the power conditioning electronics to do is convert the power output from something that looks like this to something that looks like this. And then similarly, we need a power management circuit to then convert whatever the voltage output from the battery is to whatever the load needs. So this does another conversion step to whatever the specific levels are. So if we can't overcome the threshold of the diodes that are needed to convert from AC to DC, then we can't charge the energy storage component. So that's why that was. Any questions at this point? Yeah?
I wonder, have you thought about using a solder dip of some kind to increase the mass? It might be easier than printing.
No, I haven't done that yet. The question was, have I thought about using a solder dip to increase the proof mass? I haven't thought about that. I'll have to look into it. One thing about these released cantilevers are very sensitive to lateral motion if they were to be tugged in a side direction. In using the printer, we were able to print without destroying any of the beams, but we had to be very careful to, so if this is the length of the beam, we had to print on the end and then drag the printer tip off that way so that it wouldn't put any torque on the side of the, or any moment arm on the beam. But maybe you could do something similar with that. It's a good idea.
Do you have any idea what the ratio of the lead would be versus what material you're using now?
Well, the silicon, you mean as far as densities or that kind of thing? Yeah, silicon is a density of 2,330 kilograms per meter cubed, and lead is much higher than that. This was zinc, which is sort of in the middle of those, I believe. So yeah, that could be something interesting to look into. OK, so I talked about ambient vibrations, the MEMS piezoelectric harvester, integrating the harvester and the storage, and the issues with that so far. And now I'm going to talk about optimization and then this new self-tuning design. OK, so first I did an optimization just of the harvester alone. And I did this by assuming that we would just drop the power over a load resistor instead of having any kind of power conditioning circuit. And in real life, this is sort of useless because you can't do anything with power dropped over a resistor. And this is what that power output looks like. And since it's still AC, that's why you can't charge an energy storage component. So you basically hit a brick wall here. But still, it's useful to do just a quick optimization to make sure that we're not crazy and that we can actually potentially get enough power out to effectively use the MEMS harvester to store up energy. So I did an optimization and found that if you, even on an ambient vibration source, which is why this is such a jagged plot, because it had a very ambient vibration input to the optimization, even on an ambient vibration source, you can get several microwatts out from the harvester if you have optimized dimensions. And so that's good news. That means that that it's worth investigating the next more complicated optimization. And so that you can see what that looks like. Basically, what we really need to do is optimize all three of these components together in order to get a real-world idea of what the output can be. OK, so this part gets a little, for someone who's used to circuits, this is very simple. But for anyone who doesn't see circuits very often, it might look messy. But just ask if you have questions, and I'll try to make my points clear, what I'm trying to say here. So we already mentioned that the power conditioning circuit needs to convert a signal from AC to DC, and it needs to be able to make that DC at a specific level. And so we can't just do that with a resistor. We need some sort of a circuit. So this is basically the simplest kind of circuit you can use to make that happen. And so really, this is how the energy harvester is represented electrically. This is the power conditioning circuit, and then a load, right? And this is just using a resistor on the other side of the power conditioning. So this is the simplest kind of circuit you can use. But you'll notice that the voltage and current waveforms here are out of phase. They don't line up with each other. And because power is equal to voltage times current, this ends up meaning that in some places you have negative power, and that's a loss of power. That's inefficient. So really, we would like to have not a loss of power, even though this would be a circuit that could work. So if you add a switch to this circuit, you get a whole different story. So you can see the power conditioning thing is still the same, the load is still the same, and this block is still the same. The only difference is adding a switch and then this capacitor and inductor, or resistor and inductor. So again, there are a lot of variations on this. It's just the sort of most basic way to show the point here. And so what happens if you add a switch, and if you flip that switch every time the piezo harvester gets to an extreme of travel, that corresponds to an extreme of voltage output. And what that ends up doing is shifting the voltage waveform so that it lines up, it is in phase with the current. And then when you multiply these, you get only positive power. You don't end up with negative power. The sort of catch here is that because it's a switch, it requires, and it matters when you switch it, you have to have some sort of a microcontroller to control the switching. And So that requires some amount of power. And so we have to keep in mind that this is a much more efficient circuit, but to use this circuit, we have to be generating enough power that we can sacrifice a little bit to the controller. So that's something we have to keep in mind in the optimization. So the point is, these two, the current and voltage, are out of phase. This one, the current and voltage, are in phase, and we'd rather use that more efficient circuit. So then to sort of just show a pictorial illustration of how the optimization model, what it contains, this blue outline is like what the optimization model encompasses. This represents the input energy from some, say, vibrating motor. This goes into a mechanical system that's like a spring and a mass with some losses due to damping. And then the piezoelectric material couples between electrical and mechanical domains. And then this is the power conditioning circuit, which also has some electrical losses. And then finally, some of the energy makes it to the load, or the energy storage device. And then some of it couples back into the mechanical system. And these are not to scale or anything. It's just these authors had I thought this was a really interesting way to look at the model for especially if you're not used to seeing this kind of thing. So yeah, this is the previous optimization I did essentially stopped right here and cut out this whole loop. But I guess the key point here is that since the piezoelectric harvester couples between mechanical and electrical domains, so anything you do on the electrical side affects the mechanical system, and anything on the mechanical side affects the electrical system. And the degree to which that's true depends on how good the piezoelectric material is. But it's something that means that if you're optimizing only the mechanical side, you're missing a huge part of the picture. And so this shows the whole picture, and this is the bounds of our optimization. Then the inputs to the model are the frequency and acceleration of vibration, the available volume that we're allowing ourselves to have, and material properties of the piezoelectric. And then outputs are efficiency of the system, power output, and then all the geometry and component values for this whole system. OK, so then to define what the mechanical geometry looks like, this is the big mass at the end of the harvester. This is the piezoelectric beam. This is the side we consider fixed. From the top, it looks like this. And we're allowing it to have some volume to oscillate back and forth in. And we call that side S. And then so we input an assumed volume that we're saying we're allowed to have. And then the model tells us these two dimensional values, which are the length of the beam and the thickness of the silicon layer. Those are the two parameters that we're playing with. So the model tells us that. And then this is the circuit that ends up being similar to the one with the switch. Basically, this is the piezoelectric system. These 6 arrows represent the switching that happens. This is well, there was a capacitor in the other diagram. I'm not sure if you remember, but that's analogous. And then this is, to the side of the dotted line, is the energy storage part of the circuit. And so, again, then we have a couple of assumptions. And then the model tells us all of the components of everything that's in this. So the point is, the optimization model can spit out for us the optimal design for these given inputs of whatever your vibration is and whatever size you're allowing yourself to have. And so it allows us to build a whole system that way. And this just shows if you scan the length of the cube and acceleration of the vibrations, and this is at 100 hertz, this is the sort of curve for the power output, and this is the sort of curve for effectiveness of the whole system. And one thing that you'll immediately observe is that these are not the same curve. What that means is the point where the system effectiveness is highest is not the same as when the power is the highest. That's something that's well known in energy harvesting, that max power and max efficiency don't line up. And, but it's just interesting to note. And like the visualization here is a little confusing, but the reason this drops down like this is just because I have a few physical constraints in the model that if some voltage goes higher than is physical or something unphysical happens, I set the output to 0. So that's basically what happened here, just so it makes sense. Any questions? OK. And so in general, the conclusions of this optimization were that we can get enough power even to operate this, this special circuit. We, as I just mentioned, the max effectiveness and max power are not the same. And then the really key thing here is even though we can get enough power, this all relies on knowing what the vibration is of the source that you're trying to harvest. And so if this optimized harvester is moved to a different a different vibration source, basically the output drops to like nanowatt range, essentially no power. And so really what we end up needing is a broadband or a tunable device. Because in reality, as I showed in the beginning plots of ambient vibrations, there are specific peaks you want to harvest. And if you're not lined up with those peaks, then you get almost nothing out. So the choices for this are basically to have a broadband device, in which case your magnitude suffers, or you can have a passively self-tuning device. And it's very tricky, but very interesting at the same time. I'm going to skip that because I'm getting slow in time. So I'm going to show you, this is a prototype that I developed. This is an aluminum beam, a sliding mass, and this is a shaker table and an accelerometer. And it's 30 centimeters long. And so this is different than the previous design because it's instead of a cantilever beam, it's a fixed beam. And the mass is allowed to slide instead of being fixed. So I'm going to show you a quick video of this working. So what you're seeing is the mass started at about 5.5 centimeters right here. And I'm driving this at 60 hertz, 1.8 G. And I'm not touching anything. What you see is that the beam is barely vibrating. You can kind of see it going a little bit. And the video is almost a minute long, so I'm just going to keep talking. It's a little long to show in a presentation, but I think it's really cool, so I'm showing it anyway. And these are some strain gauges at the base of the beam. You can see the mass is traveling along the beam, and it starts getting excited. And then you'll see at some point the beam, it reaches a point where it reaches the resonant frequency of the system, and the beam suddenly has a huge amplitude of vibration. And what this means is that because I mentioned how piezoelectric materials have a higher voltage output with higher strain, you essentially take a system that was producing almost no output, and you put it into resonance so that it's producing quite usable levels of output. So at this point, this is just aluminum. It doesn't have any piezoelectric material in it, but you can see how if you made this out of piezoelectric instead, it would be a very interesting energy harvester. So that is this prototype. And then just to show the experimental results from that, the black curve here shows the strain in the beam from that strain gauge, and then the red or the blue dots show the position of the mass. So you can see that, as you could see in the video, there's a marked increase in amplitude when it hits its resonant point. And then these are model results, which agree with the experiment pretty well. And then this is something Pitt, who's in the audience, has been helping with. He's built a scaled down version of that 30 centimeter harvester. This one's only 6 centimeters long. And he also has really great experimental data showing this is that little proof mass traveling along the beam. And then, again, a marked increase in strain and displacement of the beam when it hits the resonant position. So in conclusion, basically, I talked about the power requirements of the sensor node, and in our first experiments, we weren't getting enough power, but it was not optimized and not at resonance, and it was a cool proof of concept. And then in the optimized without power conditioning, we were getting a couple of microwatts. And then if you have the power conditioning system in there too, this is not including the self-tuning system. This is just the cantilever system, but you can start to get close to a microwatt. And so essentially we're there, even though it's non-trivial to integrate all these components, but the levels are starting to work out. The supply and demand of power in the system is starting to work out. So here's a quick summary and some acknowledgments. I'm going to skip over that so that I can take any questions you have. But yeah, I'd like to thank my PI is Professor Wright, and then collaborators Einar Halvorsen, Professor Mitchison, Pitt, and then I've been working also closely with Igor, and I've done work with Alec, Christine, Andrew, and funding comes from CEC and some Norway funding. So with that, I'd love to take any questions you have, and thanks for coming.
Great. Thank you, Lindsay. We'll open the floor for additional questions. You got one in the back.
Well,
since the diode drop is an important factor in the energy that you get out, and since you have a mechanical motion going on, has anyone experimented with the idea of using a mechanical commutator instead of the diodes to get the energy off that?
Yeah, there are some groups that are working on that, and it's something that I've been curious about, but it just hasn't been a focus of my research. Yeah, essentially, I think it's a really cool idea, and I think it could have a lot of promise, but it's not something I've researched on my own.
That's it, I guess. There's no more questions. Okay, great.
Thank
Thanks
you.
again, Lindsay.